All right, so welcome back everybody for the first session of the Cardiff Analysis Seminar for this calendar year. It's nice to see you all, although in 2D. Hopefully we'll meet in 3 dimensions again soon. So today we're delighted to have Yves Tourigny from Bristol, who will talk about spectral problems arising in the study of products of random matrices. So thank you very much for accepting our invitation, and over to you.
Thank you very much, Matteo. Thank you for everyone for coming to the seminar. So I personally find it difficult to understand the issues in a problem unless I've worked on it. So I suspect this is a general phenomenon. So what I'm trying to do in this seminar is to present some of the issues, the problem, so there's not going to be a lot of technicalities in this. There'll be no theorems, for instance. The definitions will be very not elementary, but maybe not complete. So it's very much about ideas rather than theorems and proofs. So here you've got the plan of the talk. There'll be 3 parts essentially. The first part is motivated by some problems that come from physics. Now, I'm no physicist, so you don't need to be afraid that I'll be talking physics to you. But my collaborators at the top of the page, Alain Conté and Christophe Texier, they work in a theoretical physics lab. More precisely, they're interested in statistical physics, and their motivations are very much coming from statistical physics. So what I try to do, what I find is interesting in our collaboration is that, well, I'm supposed to be the mathematician, so I can try to bring into the problems some bits of mathematics that may not be so well known in their community. And so to the plan then. So we start with a description of a physical problem leading to products of random matrices. The point is that in order to study the statistical behavior of the product, we can set up a certain spectral problem for the operator. Here you see it. It's called TL with a funny font. There'll be 2 different fonts for the TL, but this one is the non-random version. I will explain how this spectral problem, if you could solve it, then you would be able to deduce the behavior of the product of random matrices. This operator, which will occupy us for the talk, is non-random. It doesn't have very good properties in the sense that it's not a self-adjoint operator. Of course, the question is, what kind of spectrum can it have? So this is a difficult question. So in order to gain some insight into what we can expect from an operator like this, I'm going to consider some specific cases where we have more information about it. And we'll see that, in fact, the cases that I'll consider, in these cases, we can express this operator in terms of more familiar differential operators. But the surprise for those of you who've worked on spectral problems for differential equations will be that the auxiliary conditions that come with the differential operator are very, very unusual. So these are the 3 parts, and let's see how we get on then. So I'll turn that over. I'm sorry it's so faint, but I'll try to compensate by explaining what's there. So let's just see, maybe I can make that a bit clearer. So what I'm considering here is a transmission reflection problem for a quantum particle in a potential. So let's just see, I'll make these formulae a little bit more clear. So we're looking for here, what we're looking for is actually numbers which I denoted by RL and TL, RL for reflection, TL for transmission. So we're looking for numbers, RL and TL, they'll be complex numbers for which there will be a solution of this equation. So here, UX is a potential. The K square, that's the energy of the particle. And you imagine that the wave there's a wave incident on a sample of length L. And we want to find those complex numbers such that there will be a solution of this problem that satisfies these conditions. So we want that for x less than 0, the solution be given by this expression, and for x greater than L by that expression there. So there are conditions, you know, in order for this problem to have a solution, we will require that the solution be, for instance, continuous at 0 and L. And we'll also have some conditions on the derivatives. Now, what I want to do to make the connection with products of random matrices is to consider particular potential. So we're going to have an example. Now, this potential be somewhat unusual. It's going to be a superposition of Dirac deltas. So here we imagine that we've got some numbers uj, and we've got some, well, physicists refer to these things as impurities. So we imagine that, so if I make that to be x naught, and that I'll make that to be xn plus 1, we imagine that there are impurities in the sample at the location xj. So let's put it here. Some impurities, and in that case, actually, we can solve this this Schrödinger equation here. We can solve it in terms of a product of random matrices matrices. They're not necessarily random yet. So what I want to explain is how we can write down the solution of this equation as a product of matrices. The idea is the following: is that if you look at this subinterval here, this is a Dirac delta, meaning that it's 0 inside the interval. So inside the interval, you don't have a potential, so you just have a sort of free particle. And so the solution will be given by, so if you look at the form of this, it's simply psi double prime is equal to minus k squared psi. So we can write down the solution. So this will be valid for x in that subinterval. So we can write down the solution. So the solution of this, with this this potential here, the solution will be continuous, but will have jump. Its derivative will have jumps at the xj's. So let's write down what the solution looks like. So since the derivative will have jumps at the xj's, then there'll be a derivative from the left and derivative from the right. So here, yes, I'm interested in the solution in this interval. So we need to divide by k. Can I ask whether people can see where this is coming from, this formula?
Yeah, that's clear.
Yeah. So, and then we're going to write the formula for psi prime. So that's what we have. So if I so that means that we can express, if we put this in a vector, that means we can write, oh, sorry, yeah, that's the problem with the pen. Okay, so now if I imagine now I set x to be equal to xj plus 1, so that gives me the derivative at xj plus 1 from the left, and then I have the derivative, not the derivative, but the value at xj plus 1 that I'll be able to express in terms of the same, but at xj, not quite the same, because it'll be the, let me write it. So let's just see. So the way I've chosen it, I'll put a k there just for fun. Yeah, that'll make it easier for me. So so that will be cos. Here I'll have, now let's give that a name. This spacing here between the impurities, I'll call it theta j. So that gives me the following formula. Well, at some point I'll probably go off the page, so please tell me. So, and what we need to put here is this, right? So here I'm looking at the derivative from the left, but at the other end I'm looking at derivative from the right, and the psi is continuous, so we don't need to indicate the limit there. So so that's what happens in the subinterval, and then I need to consider what happens when I go across an impurity. So if I go from here to here, then by using the definition, so let's bring back the problem. So by using the definition of the Dirac delta, perhaps you can see that the jump, sorry, see, that's why I never work with pen, because the jump at xj will be given by this formula. All right, so so we can put that together. Let's just see. Maybe I'll write down. I'll write down this thing here in terms of matrices, so you can see what matrices arise. So if I simply write that I can write in this form. So it would be 1 here, uj here, and so on. So if I combine these two, you see that as I go across the impurities, it's equivalent to multiplying the vector psi prime psi by a matrix, a certain matrix. All right, so that's the connection between the physical problem and products of matrices. When you write down, so let's just see, maybe I can write down the formula. That will be useful, actually. So I write down yes, I didn't do it quite right. So I'm going to put a transpose here. And a transpose here. That's for technical reasons. There's nothing too deep about it, but I can write this product, this solution, I can write it in terms of a product where, so the p-ends, the pi-ends, sorry, is a product of matrices. So I'll denote the matrices by the letter G. So there'll be n of them, and the form of the jth matrix. So because I've taken the transpose, it's going to look like this. So now if I can always choose physical units so that the energy is 1. So I'm going to just write, I'm going to drop the k if you like. So what we end up with is something like this. So these are the matrices that arise from this model. And in terms of the, if I just go over the page. So in terms of the transmission coefficient, which is what we're looking for, it can be shown, in fact, there's a formula, it's quite elementary to prove, but you can show that the transmission coefficient, which is a function of L, so L is hidden in the fact that, you know, we've got n impurities, so it's hidden in a number of entries in the product. So that you can prove this formula quite easily. Here, this is, so if the meaning of this absolute value is if I take the, it's the norm of a 2x2 matrix, which we can choose. It doesn't matter what choice of norm you make. Well, sorry, it does matter for this formula, but it's not that critical. So that's this this norm is used in this formula, and that of course is the G. Right. So now, what's interesting physically is the following phenomenon, which is it's called Anderson localization. So, so Anderson wrote his famous paper in 1958. So it's a well-known paper in statistical physics. He essentially what he showed is that actually, if the matrices are, if the problem is not random, so if I imagine that these are just fixed numbers, deterministic numbers, the UJs are also fixed numbers, then the transmission coefficient, so we can measure the growth of, or the decay rather. So typically, as the sample grows, as L increases, the transmission will decrease. And but in the non-random case, the behavior of the transmission coefficient will be a non-exponential decrease. So we express that by saying that this limit is 0. By contrast, if you make the spacing between the impurities and the size of the jumps, if you make that into random variables, then this spectacular change occurs, and you find that actually there is an exponential decay of the transmission coefficient with the length of the sample. So in that case, you can show that there'll be a number gamma, which is positive, and that implies what I said, that the transmission decays exponentially with the length of the sample, meaning that if the sample is long enough, then nothing gets through, which is the localization phenomenon. Okay, so so that motivates the study of these products of random matrices. We'd like to be able to determine, for instance, the rate of growth of the product of matrices. So we come to the second part of my talk. So I'm pleased to see that there's more written on them, because I see I'm taking a lot of time over this. So this is our task. We want to study the statistical behavior of these, of objects like these. So here in what follows, X is some fixed vector. Say, if you're dealing with 2 by 2 matrices, it'll be a vector in R2. It's fixed. It doesn't matter what it is in terms of the statistical behavior, in effect, but it's useful to have it there. And these matrices will be independent and identically distributed. Now, here I just state one fact, namely that the object that gives access to the statistical behavior is this object. At least it's the definition of it. And the problem is, how can we somehow compute this function big lambda of this complex variable, which I wrote here 2L just for aesthetic reason and historical reasons, but essentially this is a function of a complex argument, but it's somewhat elusive because it's expressed as a limit. So it's not clear how you can compute it. Right. So I want to make the point that this encodes the statistical properties of the products. If we look, for example, if we calculate the derivative of this function at 0, then now let's just see. So that's the definition. So I view this as a function of L. So here we could write this exponential of logarithm of 2L times this norm. So I hope you can see that if you calculate the derivative of this famous function, and you end up with this. So that would be what would come out of it. And that would be precisely the Lyapunov exponent that I mentioned in the previous example. So that would be how, if you got hold of this function, then you could extract, for instance, the rate of growth of the product. Now let's just see. The mathematics that I'll be using, let's give credit where credit is due. So the fundamental paper on the subject is this one. It's a paper that appeared a long time ago in well, it was received by the editors in 1962. So I was about 9 months old then. So this paper is the how should I say? It's a bit of a stroke of a genius, really. It's a remarkable paper. Essentially, what Furstenberg managed to do is managed to generalize the law of large numbers to products involving products of elements in groups. And the big difficulty in generalizing the law of large numbers to that case is that, well, most groups are not commutative. And so it's not clear at all how you could succeed in generalizing the law of large numbers. And a few years later, we had another paper, which is quite important for what I want to say, which is a paper due to a Russian, Tutubalin. And what he did, he picked up the work of Furstenberg and he went a little bit further and proved the central limit theorem. And now that brings me to the second part of of what I want to say, is that a lot of the talk will be about representation theory, and I need to explain how representation theory comes into this this problem. Now here you can't see this very well, but it's some scribbling I did when I was reading the paper. Essentially, all that this scribbling indicates is that if you wanted to prove the central limit theorem for a sequence of numbers, of random numbers, the object that you would be using would be the characteristic function of the probability distribution of these numbers. And so let me write it again here. So this, if you've got a sequence of numbers which have the same distribution. So here, big X is a random variable, a numerical random variable, and with some distribution, and that would be the characteristic function associated with this distribution. And if you wanted to prove the central limit theorem, essentially you'd be working with this characteristic function. I'm not going to say much more about it, just to note that essentially what we have here is a sort of Fourier transform of the probability density function of this random variable. So we could write this as, like this. And so if f of x is the probability density function of the random variable big X, it's simply a Fourier transform of the density function. Now, so the Fourier transform, as a matter of fact, is how should I say? What I want to express is that the Fourier transform arises when you consider the representations of the group of real numbers equipped with addition. And of course, these representations, it turns out that they are exponential functions. So all this to say that when we look to have a central limit theorem for products of matrices, we'll be looking for things that play the role of exponential functions on the groups, on the group of interest. And these are precisely what the representations of the group do. The representations of a group are essentially the exponential functions of the group. Right, well, I don't know if I've done that very well, probably not, but this is how I'm trying to sell that representations are important for what we want to do. So let me now explain what a representation is. Okay, so here I'd written what I'd written. I'm repeating what I said earlier. So this is an important object if you do the central limit theorem. And when you go over to an arbitrary group, you're going to be looking for the representations of the group. They will play the part of the exponential. So a representation of a group, let's just see. G is the group. V here is a vector space, any vector space. So essentially, associated with the representation will be this vector space V, which will be called the representation space. And a representation is a map that takes an element of the group and assigns to it a linear operator acting on the vector space V. So that's what a representation is, provided it satisfies the following properties. So little e here refers to the identity element of the group. Big E refers to the identity operator acting on the vector space V. And what we have here, we require for T to be a representation, we require this property, that this property hold for every G1 and G2 in the group. And here you recognize the sort of exponential property. So this is why I was saying that a representation of a group is like an exponential. I'll give an example. Do I have an example? Yes, I will give an example later on. The important concepts for us are the following. First of all, there's the concept of reducibility. So a representation is said to be reducible if there is a non-trivial subspace of the representation space V that is invariant under every transformations TG. Yeah. And the other concept that would be important is the concept of equivalent representation. So imagine I have two representations, a T and a T tilde. Now associated with each, there'll be a representation space, which I denote like this. We say that these representations are this equivalent if there is an invertible operator between the representation space, which enables you, if you like, it's like enables you to pass from one representation to another. So these representations that are equivalent are essentially the same. So that's what this is expressing. Okay, let's see what's coming next. Right, so my famous example. Then maybe I can pause for questions before I do the example. No, okay, I'll just carry on with the example here. So what I'm going to, a lot of the talk will be about a particular family of representations of the group SL2R. Now, SL2R is just a glorified name for the group consisting of 2x2 matrices with real entries, hence the R. And what we want is that the determinant of the matrices be 1. That's special linear means the determinant is 1. So that's the group we're looking at. It's a group because if you multiply two such matrices, the determinant of the product is 1. So let me write down a very simple representation of the group. The first point is that this group acts on the vectors, for technical reasons. I'm going to exclude the 0 vector. So that's the meaning of the star here, so that I exclude the 0 vector. So let me write down the action of the group on this vector. So so if I have an element G and a vector X, then the action is simply multiplication from the right. So that would describe, and so you take your vector, the group acts on the group element acts on the vector and sends it to another vector. And we work out the formula. It's just simply a right multiplication. Okay, so that's the action of the group on R2. And then from that, we can construct a representation of the group like this. We can say that, so in order to have a representation, I need to explain, I take an arbitrary element of the group, G, and I need to assign to it a linear transformation. It'll be it'll be, yes, essentially, yes, there's a little bit of a, it'll be on R2 actually. So the star is a little bit misleading here, but sorry, I'll make that clear in a moment. I'll explain in a moment what my V is. So V, the V will be a vector space of functions actually. It'll be, there's a big V and a small v. So the big V is a vector space of functions. And these functions are functions defined on R2 and taking complex values. And I'm not asking very much of these functions. I'm asking that they be smooth. So this is now my definition of TG. TG will simply take, it will assign to V. So let me write it at length. So that would be the definition of the operator TG. And that you can check would be a representation of the group. You could check that it would satisfy the properties that I mentioned earlier. So you could check that this is, so maybe the first one is easy to check. So if I, obviously if G is the identity, then XG is X, and so TG, T of E then would be the identity operator. Are there any questions at this stage? Anything you'd like me to clarify before I move on? Okay, so I'll just carry on then. So let me make the connection between representations and my product of matrices then. So let's just see, I just need to make sure I've got my notes at hand. Okay. So, to proceed, I introduce a certain function. So now I'm going to try to make the connection between these representations and the product of matrices. So I introduce a function in my representation space. So it is this function. Okay, so this is a smooth function as long as you remember I've excluded the zero vector. So this is a nice smooth function. So it does belong to this vector space. And let's just see if I apply the representation to it. Let's see what we get. Well, by definition, this is what we're going to get. Okay, and now if I apply, if I calculate what this would be, then of course it's the same thing. So here we've got so this is the object. Let's go back maybe. Sorry, I'm a little bit disorganized with my things. So this pi n, let me go back to the definition of this lambda L, which I had earlier, so you can see where I'm going with this. Just looking for the right piece of paper. So unfortunately, I can't quite find the piece of paper I was looking for, but essentially the lambda L, you want to take the expectation of this. So let me take the expectation then. So the lambda 2L. Sorry, I got a bit confused with my moment. I'll try to get some order in my stuff. Right. I'm sorry, I'm missing that magic piece of paper. Okay, I've got it. So, okay, so, okay, I'm back here now. So, in the definition of lambda L, there is this expectation. And what we can do is to express this expectation in terms of the representation that I've introduced. So obviously, what we've got here is simply the expectation. So if I use this formula here, so we've got good. And now I'm going to use the fact that actually this is a representation. So you see it has this exponential property, so that this, you know, I can develop this. And let me just give you, so this I can write as all that applied to the same function. Okay, so here I'm using the fact that we have here a representation. And if I assume, as I do, that these are independent and identically distributed, as a matter of fact, you end up with the following. So now G is a random variable that has the same distribution as every one of these. Sorry. My notation is not great here, but and I'll do. So essentially, we've got, we can write this in this form. And so, in fact, this is the magic operator I was telling you about. So we can write this as you see that this magic operator, the operator that's featured in the spectral problem I mentioned at the very beginning, that is, in fact, an average of the representation over the group. Now, I don't think I've done that particularly well, but essentially what's going on is that, first of all, we can express this norm in terms of the representation. And then by using the representation property and the fact that we have independent, identically distributed group elements, we can express it as the nth product or the nth composition of this averaged operator. Okay, are there any questions on that? Okay. So now let's just see what's of interest. Let's just, maybe I'm going to go over here. Need a piece of paper here to do some writing. Try to. Okay, so that's where we got to. You remember that in the definition of let me write it here. This this famous function, in fact, its definition is a limit as n tends to infinity of 1 over n times the log of this thing. So let's see how this function is related to the spectrum of this operator. So the point is the following. So right, sorry. Should have been better prepared, I think. So just to, I'm writing the same equation as before. Okay, so what did we say? We said that this was the same as this operator applied n times to this particular function. Now imagine that we know the spectrum of this operator and we can develop functions in the vector space V in terms of, say, eigenfunctions of the operator. And imagine also that this operator has a dominant or a leading eigenvalue. Then if there is a leading eigenvalue, then for n large, so let me denote this leading eigenvalue. This is hypothetical, right? But we assume that there is a leading eigenvalue. Then essentially, this leading eigenvalue for n large will come to dominate. And if I now take the logarithm on both sides, then and divide by n, yeah, divide by n, we see that for n large, the this in fact is our magic function that contains the information about the statistical behavior of the product. We'll see that this this function is actually expressible in terms of the leading eigenvalue of the operator TL. So that was an important point I wanted to make. I've done my best. Okay, so this is the connection between the product of random matrices and a spectral problem. Let me pause again. Are there any questions? Okay, then. Okay.
Sorry, Yves, I'm struggling a little bit with the notation here. That what's happened to the x in all of this?
Well, the x, if you like, it enables us to work with an operator. That's why I'm not sure if that's your question, Marco.
I'm just thinking where you put this twiddles thing.
Yeah.
Somehow x has vanished.
That's right. Yeah. Okay. So indeed it has. So this is a very heuristic thing. So here I have, imagine I developed this function. And I say that actually what's going to dominate for large n will not depend on x. But, you know, it's not justified in any way.
Okay.
But there are...
This is subject to what? X is unit vector or something?
X is an arbitrary element of this magic space here. It's a fixed vector.
Right.
And so, you know, but there's, you know, the fact that we divide by n, take the logarithm, it washes out a lot of the stuff. Mm-hmm. At the end of the day, we'll only be interested in the leading eigenvalue and not on the details of the function 1L.
Okay.
But you're quite right. There's a lot there that, you know, if you wanted to make a rigorous theory, you'd have to work pretty hard.
Thanks.
Okay, thanks. So now, so we're interested. So let's just see if I can get back on my the slides that I've prepared. Okay, so okay, so that's more or less what I should have. I didn't need to write it, but we're here, as a matter of fact. Now we're going to consider this this spectral problem. So I'm looking for numbers lambda for which this will have a non-trivial solution in the space V. Now, something has happened between the last time I wrote this and now. One thing that's quite important is that the space V on the face of it consists of functions of two variables. But we need to ask, is it possible that this representation that we've got, this TG, is reducible? In fact, it is reducible. We can find an invariant subspace. So this is what I'm going to explain here. That in the vector space V, there is a subspace VL, which is the following. It's the subspace of functions that are homogeneous of degree 2L. So what does that mean? It means a function is homogeneous of degree 2L if it has this property. So if T is a number, then you have this homogeneity property. So when you apply the representation to such functions, you obtain a homogeneous function of degree 2L. And so it's an invariant subspace. And when we look at the famous function 1L that we've been looking at, it's precisely a homogeneous function of degree 2L. And so instead of working in the big vector space V, we're going to work with functions that are homogeneous of degree 2L. And such functions, in fact, although on the face of it, they depend on two variables, the fact that they're homogeneous means that actually they're completely determined by the values they take on certain curves. So we can reduce them to functions of one variable. And this is what I should be explaining to you next. Just a moment. So I'm going to explain to you how the operator that we have, on the face of it, it's an operator acting on functions of two variables, but because of the homogeneity, in fact, we can work with functions of one variable. So here's the explanation. So for instance, let me show you that if I have a function V in big V, then I claim that this function is completely determined by the values it takes when x2 is equal to 1. And we can see that by the following calculation. So sorry, I need to put an L there. So if V is homogeneous of degree L, then I can express it in this form. And then I can take the x2 out. You see? And so if I know the function on the line of equation x2 is equal to 1, then I will know the function everywhere. So rather than working with functions of two variables, we're going to work with functions of one variable. And when we work with these functions, it's equivalent to going over to another representation, which is equivalent to the first one. So this representation is called the realization of the previous representation on the line. And here I explain how it's defined. So sorry, there should be a Q, not an A. So to go from the representation TL to the representation TL tilde, you use this operator Q, which is defined here, and the effect, the equivalent representation takes this form here. So this is due to the homogeneity property. All right, I'm almost running out of time, so can I help anyone trying to understand how this representation is related to the previous one? The key here is that we're saying that if we're now going to look only at homogeneous functions of degree L, of degree 2L, then we might as well work with functions of one variable. And with these functions, this is what the representation looks like. So our spectral problem will be set let's just see. So our spectral problem, now we're going to be looking for functions, not functions of two variables, but we're going to be looking for functions of one variable. But these functions of one variable have got very unusual properties. You can show that they belong to the representation space if and only if, well, it's not an if and only if, in this case it's a necessary conditions. They have very particular behavior at infinity, which is related to the homogeneity. So this is the property. I've realized that I'm not going to have time to do everything I wanted, and I'm trying to wrap it up in 3 minutes in a way that will not leave you too depressed. Let me see then if I can wrap it up quickly. Okay. Yes. Yeah, I think what I could do then is to maybe explain what happens if I go back. So I've tried to introduce the representation theory you need to set up the spectral problem. Let me try to end by going back to the particular product of matrices that we had initially. So you remember that that's the product of matrices that describes the transmission problem I described at the beginning. So one thing you can take from what I said is that this operator, whose spectrum is of interest, is an average over the group of a representation. And for this reason, given the fact that our matrices have this form, the operator will factorize. That's one thing, one point that we can make. And if we make further assumptions, then we can actually work out what these operators are. So if, for instance, you assume that your impurities are exponentially spaced, that the spacing between two successive impurities is an exponential distribution, then for reasons that will not be clear to you, you can work out what this operator is in terms of a certain differential operator. So this is what I'm expressing at the bottom of the page here, where KL is a very specific operator. So the fact that I'm dealing with functions of one variable x now is due to this homogeneity that I've built in. So the spectral problem, then it becomes equivalent to something like this. Now this, make it bigger. So here we've got an expectation. So the spectral problem, so lambda is the eigenvalue and f is now the is the unknown function. So the spectral problem will take this form. And at this point, you can maybe see, if you've got a lot of experience in applied maths, you can see that you can, this is just a shift. So u is a random variable. You take the expectation of that shift here, and that if you go over to the Fourier transform, if you, instead of working with f of x, you work with this Fourier transform, you'll be able to reduce that to a differential equation. In this way, you get a differential, you get a spectral problem that is expressible in terms of a differential equation for the Fourier transform. And the difficulty is to determine when your function f hat does belong to is a Fourier transform of a function in your representation space. And that's a problem that we have solved. And so we are able to say something for this product. We are able to say something about the statistical behavior of the product. I'm afraid I've gone over time. Maybe I'll stop, and maybe with some questions I can make good all the bad that I've done.
Thank you very much. So are there any questions for Yves?
So even this part at the end that you were trying to explain in a bit of a hurry, are you saying that the difficulty at the end is to understand whether a given function f hat lies in the domain of the operator?
That yes, the domain being defined in terms of the representation space.
Mm-hmm.
So, so to summarize, you're right, Marco. So to summarize, you do eventually obtain a differential equation for the eigenvectors. But if suppose you can write down the general solution of this differential equation, you wouldn't know which member of the general solution belongs to the representation space unless you made a special analysis.
Mm-hmm.
So yes, the domain of the operator would be contrived to be in terms of the representation space.
And this is true even once you've imposed on your the solutions of your differential equation restrictions, like I don't know, that you want them to be in L2, for example. Even after doing that, you still have additional.
That's right. That's right. Maybe
have to be satisfied.
I'm glad you asked that point. Maybe I can go back to something I really skimmed over, which is a point that we managed to understand, but I didn't manage to explain. Okay. So I went very quickly on the business of homogeneity, but essentially, if we look at this lemma here, let me make it bigger. So now I'm working with VL tilde. So that's my representation space now. So I'll be looking for, I want my eigenvectors to belong to that space. And how do I know that a function of a real variable with complex values belongs to it? So that's the question. And I know that it belongs to it if it has the following asymptotic behavior at infinity. So here L is a number. And it's for V tilde to belong to this representation space, the behavior at infinity is going to be very special. These two limits have got to exist and be equal. So this is, if you like, very unusual. It's not something you could express in terms of integrability, for instance.
Mm-hmm.
This is where the unusual features of the spectral problems come in. So that I think addresses your question. It's not just a case of it's got to be integrable in some sense.
Yeah, it'd be interesting to think about if you take the operator without having these restrictions,
yeah,
you'd get an extension of the operator.
Yeah.
And then I guess one would want to look at the deficiency indices for the restricted operator relative to that larger one.
Yeah.
And I mean, that looks like a rank 1 condition there. Well, no, maybe it's rank, it's hard to say. You want the two things to exist, and then you want them to be equal.
Yeah.
And
I'll
you're not even guaranteed that they exist.
Well, I mean, well, you'd only select the solutions for which the limit exists. Then you'll want to verify whether the limits are equal.
Yes.
Does that make sense?
Yeah, I think it looks like I think it's a rank 2 condition. So it looks like deficiency indices 2.
Maybe now I was never going to attempt this in the time given, but maybe I can try to explain how this would relate to things like the Weil coefficient. So once you go over to the Fourier transform, so I'll say it in words. If you go over to the Fourier transform, well, maybe I can make use of the visualizer. So imagine I have some operator. Suppose I've reduced my problem to something like this. Whoops, sorry. I've got some differential operator. I've got my my eigenvalue here, and I'm working in Fourier space. Now, the problem with the functions that I'll be looking for will certainly have a problem at 0. So what this differential equation, it will be valid only if S is not 0. Otherwise, because if you remember what I had on the previous slide, you see that the behavior of the V's at infinity is algebraic. So that when you go over to the Fourier transform, they're not very nice functions at the origin. The Fourier transforms of algebraically decaying functions have got a problem at S is equal to 0. So what would happen is that in order to solve the spectral problem, you need to separate the problem into 2 parts. You'd have a plus part and you'd have a minus part. Now, the Fourier transforms will be well behaved at infinity. They'll be decaying because the original functions of X are smooth. So the Fourier transform will certainly be decaying. So you'll be able to find decaying solutions or values of, values of lambda. Well, you'll be able to find decaying solutions, and there'll be some Weil coefficient associated with the plus part, and there'll be a Weil coefficient associated with the minus part. And the spectrum is obtained by asking that the two be equal. So that's how we can relate. We haven't got a proof of that, but we think this is what's happening. That the spectrum that is of interest to us is, if you could get hold of the individual Weil coefficients, this is how you could find it.
Okay, yeah, that's clear. Yeah, thanks. Yeah, that's very clear.
I'm sorry I couldn't go into it. I know that for you guys, this is the interesting part. I was all in love with this representation theory thing, but I didn't quite get to the thing that would be of more familiar to you.
Thanks for that. Any further questions for Yves? So if not, let's thank Yves again and move to the formal bit of the seminar. Just a reminder, next week we will have an in-person seminar. So for those of you who want to attend in person, we'll be in the usual seminar room and we'll be broadcasting the seminar via Zoom as always. So thanks, Yves again.
Thank you.